So in the last video we stopped here, and let's continue talking about the moment generating function, and I want to explain again from this part right here. So if we if we'll derive the moment generating function twice, which is this is the moment generating function, so let's derive it twice. So we have deriving it twice according to theta. So note here that when we take the derivative with respect to 1 is just a constant, we'll get 0, plus when we take we're taking the second derivative. So to take the second derivative is to say that we are deriving this part here before we put instead of theta 0. So this is the second derivative, the first derivative, and let's derive it again. So deriving the expectation of x, which is a constant, will give us 0, plus deriving the second term, 2 over 2 factorial is 1 times theta is theta. So to derive theta by theta is 1, we will be left with the expectation of x squared, plus here we have 3 times the derivation of theta square will be 2 theta over 3 factorial times e to the x to the third, plus many other terms. So now, like in the calculation of the first moment, all we have to do is to put instead of theta 0, and when we do that, you will notice that this term theta equals 0, this whole term will go away. Also all these other terms here which contains theta will go to 0, and we will be left with this term right here, the expectation of x squared, which is the second moment. So if we'll continue to do this, we'll get more and more moments of the function, and you can know all of them. So the basic idea is just to calculate. Let's do it by steps. The first thing is to calculate the moment generating function, which is to take the expectation of e to the theta x. This is the first part, and the second part is after you did this calculation and you got the moment generating function, all you need to do in order to get the moment of the function is to make the derivation according to the moment you want to find. So if you derive the moment generating function once with respect to theta, you will get the first moment. If you'll derive it twice, you will get the second moment. And of course, if you will make three derivatives, you will get, of course, the third moment of our function. And let's take a small example. Let's talk about x, which is normally distributed with mean of 0 and variance of 1. So let's compute its moment generating function. So we know that the moment generating function is the expectation of e to the theta x. So this expectation, because x is normally distributed, is the integral from minus infinity to infinity of e to the theta x times the density function 1 over the square root of 2 pi times e to the minus 1/2 times x over, x times x squared dx. So we know that we can write this as the integral from minus infinity to infinity of 1 over square root of 2 pi times the exponential of theta x minus 1/2 x squared dx. And now I would like to make a little bit of change in the exponential. That is, instead of writing it like this, I will write it as let's see, 1/2. It's the same as 1/2 x minus theta plus square plus 1/2 theta square. And let's just check it out. We have here minus 1/2 of x squared minus 2 theta x plus theta squared plus 1/2 of theta squared. So we have minus 1/2 x squared plus theta x minus 1/2 of theta squared plus 1/2 of theta squared, and these two are cancelled one with another, and we get this back. Okay, so it's okay. So we can write this as integral from minus infinity to infinity of 1 over square root of 2 pi times e to the, instead of this part, we're going to write minus 1/2 x minus theta squared plus 1 over 2 theta squared dx. So because we don't have any x here, we can pull it out of the integral, so we can write it as e to the 1/2 theta squared times the integral from minus infinity to infinity of 1 over 2 pi times e to the minus 1/2 x minus theta squared dx. And now we you have to take a good look on this integral. I claim that it is just equal 1, because if we say that x will what essentially we have here is a parameter x which is normally distributed with the mean of theta and variance of 1, and we take the integral over his over its density function, which will give us 1. So this is basically 1, and we have e to the 1/2 theta squared times 1, which is e to the 1/2 theta squared. So in conclusion, we saw that we have a variable which is normally distributed with mean of 0 and variance 1, and we find that his moment generating function is equal to e to the 1/2 theta squared. So this is for now about moment generating functions, and I'll see you next lesson. Bye bye.